Hi again everyone. In this video we're going to continue our look at vector fields and some of the basic operations of vector calculus. Now in a previous video I introduced the concept of a vector field and we discussed the need for a vector field and we sketched some graph type vectors associated with particular vector fields. Now in this video we're going to talk about the so-called divergence of a vector field. Now divergence is one of the basic operations from vector calculus and loosely speaking it's a kind of derivative. Okay, well in previous lectures we introduced the gradient field of a scalar valued function f and we wrote it like this and would call it grad f. Now, the divergence is kind of like a complementary idea to the gradient of a function. And to kind of write this with similar notation, this triangle from when we looked at the gradient, I'm going to introduce this vector differential operator. So you can see here I've got d dx, d dy, d dz. They're all partial differential operators, and ij and k. Now it looks like this is a vector, but really it's not. It's a symbolic vector, and the point is that this can operate on various functions or vector fields. Okay, so this triangle will be referred to as the del operator or just del. Okay, well, let's introduce a basic definition involving flux density and divergence of a vector field in the plane. So suppose m and n are each, say, functions of two variables, then we can define the divergence, also called the flux density, of a vector field at some point. It's just the sum of these partial derivatives. Now, to write that in terms of our del operator, I can use the dot product or the scalar product. So here I've got del dotted with my vector field f. So if I just write this out, now because we're working in the plane here, my del will just, I can just write it using d dx and d dy. And I'm going to dot that with these component functions of my vector field f. So how do you expand this? Well, think of it as a regular dot product, but instead of multiplying, these d dx, d dy are operating on these functions of x and y. So it would be d dx of m, which is just dm dx, plus d dy of n, which is dn dy. Okay, so I can write the divergence of a vector field in two ways using div f, or if I want to use the del operator, it's del dot f. Okay, well, like I said before, loosely speaking, the divergence of a vector field may be thought of as a type of derivative of from vector calculus. Now, just a side note, how does this relate to the gradient of a vector field? Well, remember, the gradient field of a function is just a vector field with partial derivatives as components in the vector field. Okay, so you can think with this notation here, you can think of taking this symbolic vector and multiplying through by the scalar function f. So in this kind of notation up here, and this thing here, you can think, all right, well, I've got d dx, d dy, d dz, and I'm multiplying in a loose sense by f. So this is a scalar, this is a vector. What do we do? Well, this will go into every component and form the gradient vector that we would expect. Okay, so that's how the del works with the f with this notation. Okay, the subscripts up here, of course, this is df dx, this is df dy, this is df dz. Okay, so back to the divergence. Well, suppose I've got, that was working in the plane. Suppose I've got a vector field in three-dimensional space. So f sub 1, f sub 2, and f sub 3 are all functions of three variables, x, y, and z. Well, it's very similar. Essentially, it's just the following. So again, writing it as a dot product, you expand this component with this component, this component with this component, and this component with this component, and then add them all up. So essentially, you're going to get the following. Okay? All right, well, let's calculate the divergence of a few given vector fields. So for this particular vector field, we know that the divergence is just this dot product. So let's write this out and watch the operations on the corresponding component. So ddx of this function plus ddy of this function. So ddx of this, when I differentiate partially, I hold the y constant and differentiate with respect to x. So I'm going to get something like 3x squared y for the first part. And then ddy of y times x squared, well, differentiate with respect to y and hold x fixed. It's going to become a positive x squared. And similarly, let's look at this more general case. In this case, I've got the following. So it's ddx of cosine z, well, that's going to be 0 because there's no x's in there, plus ddy of sine y. Well, if I differentiate sine y with respect to y, I'm going to get cosine y, plus ddz of tan x. So there's no z's in that, so that's going to be 0. So I get cosine y. Okay, well, you can see in our answers, hopefully, that these are just real valued or scalar valued functions. So in each case, we started with a vector field. We calculated the divergence and we got not vector fields, we got scalar valued functions, real valued functions. So that's one of the properties of divergence. The divergence of a vector field will always be, a scalar valued expression. Okay, so here's another example that I've prepared earlier. Again, just very similar to these two. It's quite easy to calculate the divergence, but what does it actually mean? Well, suppose I compute the divergence of some vector field at some point. Loosely speaking, this is just a measure at which the vector field spreads away from the point P. And the spreading away can be measured by the flux or the flow rate out of a small closed surface surrounding P, like a box or a ball centered at P. Okay, so here I've drawn in some basic vector fields, and the idea is to try to get a geometric feeling for the divergence of each vector field. Well, let's just draw this circle in around the origin. And let's look at some of the arrows associated with the vector field. Well, you can see that over this circle, the arrows are all sort of pointing out. There's going to be a net outflow out of that circle. So we would predict that the divergence is positive at the origin. And in fact, if you calculate the divergence of this vector field, well, it's positive too. So that sort of confirms what we would expect from our diagram. If you look at this particular circle, this is sort of drawn somewhere else, you can see there's some inflow into the circle, but there's much more outflow. So there would be a net outflow out of this circle. And that's true for any circle in the plane. Okay, so again, we would expect the divergence to be positive. Here's another example. So here the vector field is the following. Just to save space, I haven't written out the vector field using I and J notation here. Sometimes I'll use these ordered doubles. Okay, well, let's draw a circle around the origin. I can see, well, the vector field, there's a net inflow into the vector into this circle. Okay, so at least at the origin, we would predict that the divergence of this vector field is negative. And again, let's draw another circle somewhere else. We can see there's much more inflow than outflow out of this circle. So again, we would expect the divergence at all points inside this circle to be negative. And in fact, if you calculate the divergence, it's -4. So it's a constant no matter where you are in the plane. Okay, here's another example. Here the vector field is the following. Let's draw a circle around the origin, keep it simple. Now you can see there's some inflow, but there's also an equal amount of outflow over the edge of the circle. So the inflow and the outflow cancel each other out. So you would say that the divergence at the origin is neither positive nor negative, it's 0. And similar with this particular circle here. And again, if you calculate the divergence, you'll see that it's 0. So that gives you some indication on what the divergence means and the sort of concept of spreading away from a point. Here the vector field wants to spread away from the origin and all the other points. Okay, that means the divergence is positive. Here the vector field wants to collapse or not spread away from every point. It wants to sort of come to each point. So in this particular example, the divergence would be negative. And here, well, the vector field doesn't really want to spread away or approach a point. So here the actual net spread is 0. So the divergence would be 0. Okay, so if we, for example, imagine F to be the velocity field of a gas or fluid, then the divergence represents the rate of expansion per unit volume under the flow of the gas or fluid. And like I said before, if the divergence is positive at some point P, then there's a net outflow over any small closed surface enclosing P. And we call P a source. So in this particular example, say the origin would be a source. Okay. If the divergence is negative at a point, then there's a net inflow over, I guess over is a better word here, over any small closed surface enclosing P. I mean, we would call the point P a sink. So you can see here, for example, the origin would be a sink for this particular vector field. Okay, so the divergence at a point P measures the net rate of change with respect to time of the mass of gas or fluid flowing from the point per unit volume. Okay, so here's some simple pictures of what I've just said. Here, a gas, the divergence is positive, the gas is expanding at the point of interest. And we would call that point a source. Here the divergence at this point is negative, so the gas is compressing at that point. We would call that point a sink. Now, if the divergence is 0, then we call the vector field F incompressible. And you may have heard of, for example, incompressible fluids. Well, mathematically speaking, this is what we mean when we talk about an incompressible vector field. Okay, so here's a basic example involving a field plot that I have used, I've drawn using Maple. So the command is field plot. Now, vector fields are quite hard to draw, but for this particular example, we don't actually know what the vector field is, but we've got the arrows associated with it drawn in. So let's have a look at the origin and see what happens with the divergence, if we can predict what the divergence is going to, the sign of the divergence at the origin. Okay, so let's just draw a basic, okay, a badly drawn circle. Now, let's have a look at the expansion or the compression of the vector field, the measure of spread of the vector field over this closed curve. So you can see there's going to be lots of inflow, and I can't see any outflow, so there will be a positive net inflow into this particular circle. And so for each point in that circle, the divergence of the vector field would be negative. So let's just choose, say, the origin. Since there is a net inflow, positive net inflow over the circle. Okay, and what you might want to do is just draw a few more circles and see what happens. Well, essentially, if I draw a circle down here, you'll see that there's some outflow, but there's more inflow. So there would be the divergence of this vector field is negative at every point. All right, here's another example. I've got a vector field in the xy plane given by this expression here, and we can think of this vector field as, say, representing the velocity field of a fluid. We're asked to draw a square centered around the origin and analyze the flow over the boundary of that square, or the edges, and predict whether the fluid is expanding, compressing, or neither. And like I said before, when there's neither expansion nor compression, we call the vector field incompressible. Okay, well, it's easy to, of course, calculate the divergence directly from this vector field. Divergence will be 1. Okay, so and that's for all points. So you would expect the vector field to be expanding at all points. The fluid is expanding at all points. Okay, but let's actually put some a nice picture together and kind of confirm the positivity of the divergence from our graph. So let's draw in our rectangle, and let's draw in some of the vectors associated with our vector field. Well, this is just a multiple of I, so and there's no j component here. So essentially, the vectors associated with this vector field will be horizontal. Now, if x is positive, then I'm just going to get multiples of I that point in the same direction as the unit vector I. If x is negative, well, I'll get vectors that are pointing in the opposite direction to I. And as I move, as x increases, the magnitude of these vectors increase. As x sort of gets larger, magnitude of these vectors will also increase. So along this particular line segment, x is constant. So the vectors associated with v will look something like that. Let's go over here. X is negative here, so they'll just be sort of pointing in the same direction as negative I. And along these lines, well, you might have something like this. So let's have a look at the flow over the boundary. Well, you can see over this edge, there's a net outflow. Okay, so over this edge, there's also a net outflow. Over the top edge and the bottom edge, there's neither an inflow nor an outflow. So there's no flow over here, there's no flow over here, there's across it, there's no flow across here, there's no flow across here. There's definitely a positive flow out over this side and a positive flow out over this side. So combining this and this, we see that must be a positive net outflow over the boundary of the square. So over the two vertical sides, there's positive outflow and zero flow across the horizontal sides. Okay, so what do we conclude? Hence, we must have positive net outflow and so the divergence of the vector field, say at 0 at the origin, is positive. Now of course you could just calculate that and go, well, the divergence is 1 everywhere, so it's got to be positive everywhere. That's not the point of this question. So what do we conclude then? Well, our fluid is expanding at the origin. Okay. Now, if we think of our divergence, the divergence as some kind of, very loosely speaking, derivative, well, you would expect some basic properties of that derivative. So this is what the point of this slide is. So essentially, if you've got two vector fields added together and you take the divergence, well, you can take the divergence individually and add them together. So this is like a sum rule. Here, in the second expression, this is like a product rule. You can see I've got a scalar valued function, phi, multiplied with a vector field, f. If I take the divergence of the product, well, it's phi times the divergence of f plus f dotted with the gradient of phi. And here's another reasonably useful identity. Now, you may have heard of the Laplacian. This is just a combination of the divergence and the gradient. So you start with a scalar field, phi, some scalar valued function. You take the gradient of it to form some vector, and then you take the divergence of that gradient field. Okay, so writing it in terms of the del operator, it's del dotted with grad phi. Now, it's easy to prove these. All you do is basically start with the left-hand side, write out the components of your vector field or your function, and then try to come up with the right-hand side. So I'm not going to prove them, but I encourage you to try to prove these identities. Okay, well, we've looked at how to calculate the divergence, and we've got a little bit of geometric understanding of the divergence, but what I want to do now is discuss the idea of relating the divergence with flux, the so-called flux density. So when I'm talking about flux density, suppose I've got some rectangle here. Essentially, when I mention the flux density, I mean the flux or the flow rate across the edges of the rectangle, so boundary, divided by the area of the rectangle. Now, essentially, so if we're working in a plane, the divergence is just the limit of this as the area of the rectangle approaches zero. So you sort of shrink the sides, and you sort of shrink this rectangle towards this point here. If we do that, then we come up with the divergence of f evaluated at this point. So let me show you how that comes about. So we're just going to work in the plane for simplicity. So suppose I've got a vector field with m and n as the component functions. Okay, and m and n are well-behaved functions, and they are functions of two variables, say. And let's just say this f is the velocity field of a fluid in the plane. Okay, so essentially, to calculate the flux across the boundary of the rectangle, we are going to look at the flux across each edge and then just sum up each of those flow rates or exit rates. Okay, so in two dimensions, we would speak. So if this is the velocity field of some fluid, we would measure the flux in area per unit time. Okay. So the next question is, how do we actually measure the exit rates or the flow rates over the edges? Well, let me just give you sort of a general idea, and then we'll sort of use that idea on each of these edges. It's very simple because actually they're parallel to either the x-axis or the y-axis. Now, let me just draw in some sort of curve here. Okay, and suppose that the curve has length L. Now, at every point on that curve, the vector field has some sort of vector value, and to measure the flow, say from this side to this side of the vector field over that curve, what I'm going to do is choose some point on that curve, look at the value of the vector field there, and I can also produce some unit normal to the curve. Okay, so now what I can look at is actually the component of my vector field in the direction of that unit normal. Okay, so this length here is, in this picture at least, the component of my vector field in the direction of the unit normal to this curve. Okay, and I can compute that by just taking the dot product of f with this unit normal vector. Now, as long as L, the length of this curve, is not very large, and as long as f is well behaved, then basically f won't change much over this this little curve, and neither will this normal vector. So essentially, as an approximation to the flow rate over this curve, an approximation would be this distance, f dotted with n hat, times the length of the actual curve. Okay, so let's write that down. So the rate at which fluid crosses, okay, in this picture it's sort of going from this side to this side. The curve is approximately equal to this distance times the length of the curve. Okay, so I've just chosen a sample point there, and essentially, so this is just at this sample point, somewhere on the curve. Okay, so the important thing there is you need a unit normal vector. Now what we're going to do is look at the flow or exit rates over each of these curves using the idea of this unit normal vector and the length of the curve and the sample point. Okay, so let's see if we can relate it back to our picture over here. So let's start with, say, labeling the sides. Let's take this side as, say, S1, this side as S2, this side as S3, and this bottom edge as, say, S4. Okay, so let's look at the exit rate over this side here. Well, what do I need? Firstly, I need to choose a sample point on this curve. I'm going to choose it to be this point here, and you'll see why in a minute. The length of this curve is delta y, and what is a unit normal vector to this particular vertical edge? Well, that's easy. It's just the I vector. Okay, so essentially, this is my sample point, this is my unit vector, and the length is just delta y. So what I'm going to do then is evaluate f at this point, my sample point, dot that with my unit vector, my unit normal vector, and multiply by delta y. Okay, now we know, let's just sort of write this out in terms of the component functions. Then that's just the following. Okay, now if we take this dot product, well, this is just the I vector here, so I dotted with j, that's 0, I dotted with I, that's 1. So actually, what we're going to be left with is just m evaluated at the point times delta y. Okay, so that's an approximation. And it'll be a reasonable approximation as long as delta y is not too large, okay, as long as it's sufficiently small. Okay, so let's have a look at the exit rate, say, over S2 now. Okay, well, same thing again. We basically got to choose a sample point on this edge somewhere, find a unit normal pointing in the outward direction, take the dot product and multiply by the length. Okay, so I'm going to actually choose this point as my sample point, and the question is, what is a outward pointing unit normal to this edge? Well, it's going to be J. So if I draw in my unit normal vector there, so essentially using this, it's just f evaluated at this point dotted with j times delta x. Okay, now if you write it out again, what will happen is you'll see that very similar to the case up here, essentially you'll get the j's dotting through to give 1, and the when you dot the j through with this I, that'll just be 0. So essentially you'll get the following. Okay, and what about, say, the side S3? What's an approximation for the exit rate over there? Well, let's choose a sample point. I'm going to choose this point here. What's a unit vector, a unit normal vector? Well, minus I. And so essentially you want to dot f at this point with minus I and times by the length delta y. So if you do that, you'll get the following. Okay, again, if you go through and work out this dot product in terms of these component functions, you'll get minus m x comma y times delta y. And lastly, what about this side S4? Well, I'm going to choose the same sample point as before, and this is going to be my normal vector minus j. So I guess over is a better word to it. S4. Okay, times that by the length delta x. And if I expand that, the dot product in terms of the component function, then I'll get the following. Okay, so I spent a fair bit of time there explaining how we come up with these approximations for the exit rates or the flow rates over each side. Let's sum up those flow rates. Okay, now if I add this and this, you can see I've got a common factor of delta y. If I sum this and this, I've got a common factor of delta x. So let's see if we can use that. Okay. So the flux across the boundary of our rectangular region is approximately equal to the sum of this, 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 and this. Now, if I add this and this and take out the common factor, so it's just a comma here. And if I add this and this, take out the common factor, then you can see, well, if I kind of divide and multiply, say in the first term by delta x, well, this, for delta x small, this is going to be approximately equal to the partial derivative of m with respect to x. And if I sort of insert a delta y into the second term, this is then, for delta y small, this is going to be approximately equal to the partial derivative dn dy. Okay? So I can replace this with dm dx. I can replace this with approximately equal to with dn dy, and you'll see I've got a common factor here of delta x delta y. Now, what is this product here? It's just the area of this rectangle. So the flux density then is approximately equal to basically the divergence, because I can bring this to the other side. So essentially, using this up here, the flux across the rectangle boundary is approximately equal to this. The area is delta x delta y. When I divide in, that delta x delta y will be cancelled out. And what we do is we essentially let delta x and delta y go to 0. So I shrink the rectangle down towards this point. So this is just the divergence of f at the point of interest. Okay, well that's a derivation of what the divergence actually means. Essentially, it's the flux density, say, of this rectangle as the area of the rectangle tends to 0. That's what when you calculate the divergence at a point, you get a value. That's what that value is. It's the limit of this flux density.